Okay, so we've created a MCF file. When we created those, I quickly jumped over all the parameters of the axis. So if you look at the x-axis, for example, you see a couple of parameters, the limits, and most importantly, parameters that influence the cycle time calculation and the motion planning capabilities of CSE, like speed, acceleration, deceleration, and so on. The question is, how do you obtain those values and what to feed in here? Many times you can get those values from the machine tool vendor, or should ask for that. That's the easiest. Many fact sheets about the machine that you can download from the internet contain rough values with the maximum speeds and accelerations of those axes. Also, I guess your customer will be able to tell you those values. If you don't care so much about very accurate cycle time calculation, or also if you feel that in the motion planning the accuracy does not play that big role, so if you accelerate two axes at the same time, would that probably cause interference issues if the acceleration factors are not correct? If you don't care so much, you can leave it on the default. Then of course you shouldn't look at the time calculation that CSE provides. That will be wrong. If you want to have exact time calculations, you should really make sure that you fill in most of these values correctly. Like I said, the easiest thing is to ask the machine tool vendor or ask your customers to provide those values. For the Siemens 840D, there is a way to obtain those values by asking your customer to send you a so-called archive file. That's basically a backup of the whole controller configuration that you can produce on the real machine. So on the real machine, you select a function in the user interface that allows you to back up all the machine parameter. The customer can send you this file, and then you can obtain the parameters from this file. To be able to, I will show you how to do that based on the 840D in the session. Before we dive into the details, and that's going to be a little bit more complicated, I have to explain you a little bit about the concept of axis in the machine in the 840D. So first of all, this probably looks confusing if you look at it for the very first time, but in the end I think it's pretty logical. The basic idea is that every machine has a limited number of machine axes. So these are really global axes that are available across channels, so these are really independent of the channels. That lists all the axes that can be controlled by the 840D. On the 840D, that is limited to maximum 32 axes. On the simpler versions, probably even, I think it's 20 or so. But at maximum, these are 32 axes. Each axis does have an axis number. You can also find out what type of axis it is, if it's a linear axis or rotational axis. For the rotational axis, you have an additional parameter that tells you whether it can rotate infinitely or whether it has limits. That of course has no meaning for linear axis, just for rotary axis. And then the next thing that you can see is the blue and the orange sides that should represent two channels of these machines. So here you can assign an axis to a certain channel. Also in the axis, in the channel, the axis can have a different name, a different index, and what we are actually looking for. Here you can also find the parameters about maximum velocity, acceleration, limits, and so on. What you also find here is every channel has at least two, for most milling machines for sure 3 so-called geo-axes. Geo-axes represent the axes that move if you just program X, Y, or Z in the NC program, and the direction of those axes also determine, for example, what G17 means. So by the direction of the X and Y axis, it is determined what the plane for circles, for example, is. In addition, and like I said, you can have a separate configuration per channel that picks different axes from the machine axis lists and makes them available in this channel upon initialization. Spindles, that refers to tool spindles and workpiece spindles, are first of all defined as a typical axis, so you will find a spindle also in the axis configuration, and it's also linked to a spindle configuration. That spindle configuration is also global. You can have up to 10 spindles defined in the machine and link that. We will see that a little bit later on if we get to spindles. So a little bit theory. Now let's look into how to obtain those values. To make your life easier, I've created a spreadsheet, an Excel spreadsheet, with some instructions on how to do that. There are also instructions available to tell your customer how to get this archive file from the machine. Once you have that file, you can go into this table. It will show you which machine parameter you have to look up in the archive. It provides you ways to calculate the correct unit. So, for example, on the real machine, the machine datum for the cycle time for the eProduct is stored in second. Machine configurator wants to have it in the unit milliseconds. So, if you type in the correct value here in the light blue field, you will get the value in the correct unit for machine tool configurator, and you can just copy and paste the value over here. So that's about theory. What I will do now is to open an archive file. I will open it with Notepad++. That's the editor that I have available. It's free of charge available, and it provides powerful search capabilities. So the first thing I will look up is the machine datum that includes the eProduct. I can either search for this name. In most cases it's easier to just search for the number since it's easier to type. So I will search for 10,050, find it, and then I already find this number. So I can type in 0.002. and directly use that. Okay. The next number is the circle precision that determines the maximum deviation from the radius for the start point and for the end point, and what deviation the controller allows here. That is 0.01. Oh, okay, that's already filled out. Nice. The next one is for the look ahead. That's 200 blocks. So I can type in 200 here. Yeah, and these values you can then just type into machine configurator. The more relevant data is really about axes and spindles, and here the table gets a little bit more complex. So first of all, I will have to look up what machine axes do exist. That's stored in machine datum 10,000. So I will search for 10,000. That's the wrong one. To make my life easier, I will find all and then make a double click here, and then I'm in the right section. So this machine datum 10,000 is an array. So it has, like I said, the Siemens controller is limited to 32 axes. Actually, it says 31 here. And from here you can see which axes are available in the machine. So that's X1, Y1, Z1, and so on. And these values that I find here, I will just copy in here. So X1, Y1, Z1 is already correct. Then we have SP1. I would guess that this is the tool spindle in my Hermle machine. Then we have C1 and A1. And A1. And Finally, we have U1 and Mag1. I would guess that I don't need those ones, since to simulate the machine having the table with A1 and C1. Oh, I skipped one. B1 is of course not correct, so after SP1 we have C1, A1, U and Mag1, and this one I can delete. So for the simulation, only those 6 here are relevant. Those 6 ones are relevant. U and Mag1 I don't really need. The next one is an axis number or axis qualifier. That's 10,002. In all machines that I've seen so far, these are really numbered. Theoretically this can change, so check it, but in most cases you can just take over the default values. The next value is 30,300. Okay, here I found the correct section for the rotary axis. And to find out which axis is linear or rotary. So 0 means it's a linear axis, 1 means it's a rotary axis. So what you would want to do is look up this machine datum for the correct x1 axis that corresponds to my x1 axis, and look up it's a 0. Okay, so this means it's a linear axis. AX2 is y1, it's also linear. The next one is z1, it's a linear, that's correct. x4 is my spindle, that is a rotary axis. Okay, so that's also correct. x5 is a rotary, ax6 is a rotary, and ax7 and ax8 as well. So that's already filled out correctly. Next thing is to look which of the rotary axes are modulo axes or which can turn infinitely. So that can be found in 3310. Okay, that's a little bit inconvenient because all the results are not in one block. To find that, you can use in Notepad the find all in current document. That will produce here this search results from all the lines that are found, and then you have it really in one block and just look up the numbers. So for x4 it's 1, so that is a infinite spinning axis. x5 as well, so that I need to change. So that means my C axis in the table of my Hermle machine is a modulo axis. And x6 and x7 are not, and x8 is again. So x6 and x7 are no modulo axis, x8 is again. Okay, so that's correct. Then we can look up 3500. I'll use the same mechanism. So x4 is 1, x4 is 1, and all the others are 0. That's correct. Just one spindle in this machine. Makes sense. So now we come to so that was preparation, so that I just know which axes do exist. The next thing is really to look up the values. I will just do that for the velocity and the acceleration. All the other values that you find here can be done really in a similar way, and then we can save some time. So I will search for 32,000, find all, and then I can see those values for up to 8 axes. So we have 60,000, 60,000, 60,000, x4 is 10,000. Then 65, 25, 25, and the last one is 42. That's the magazine. And then also here, the unit that you find in the machine datums and the unit that you have to use in machine configurator are different. So that's why we do here a conversion. This conversion takes into account if it's a linear or a rotary axis. So in the rotary axis, the conversion from revolutions per minute into degree per second is of course different than from millimeter per minute into millimeter per second. And like I said, you do the same thing also for the acceleration and all the other values. Like I said before, for the axis limits you don't have to take care about, since CSE and NX doesn't consider those values from machine configurator. It uses the axis limits defined in the kinematics model, so that doesn't make a huge difference. So assume you have filled out this table. The next thing would be to copy those values into machine configurator. One question that probably might come up: the machine axis names here are different than how I named that. If you later on want to simulate something with VNCK, it's really mandatory that the axis names that you use in your kinematics model really fit to the machine axis names. For CSE simulation, if you use emulated controllers, that is not really required. Actually, it makes your life easier if you stick to the default names X, Y, Z, A, B, C, U, V, W, and S. That makes your life easier, since then you can use the default configurations or the default implementations from the CCF files. If you don't use these names and instead you would rename your axis and call it, instead of X, call it X1 and Y would be Y1, then you would have to make more customizations. That's not a lot of effort, but it can save some time. So for the x-axis, I will just copy over those values. So for the velocity, that's as indicated here. For the velocity, this value would be copied to maximum speed. So 1000 should be here. The max acceleration is 10,000. The Siemens controller does not differentiate between acceleration and deceleration. Makes sense. So you can use the same value. Fine precision, that is related to the exact stop behavior. We will talk about that later in the motion planning section. So that's for fine, it's 0.032, and for coarse it's 1.0. Okay. The jerk is 30,000. The jumpability is 4. And the KVI factor is also 2. So now you've configured the axis, and now CSE should really provide you with the correct cycle time calculation. Of course, you will have to do that for all the axes as well, but that's a way how to obtain the velocity profiles and all the parameters for the axis from a Siemens archive. If you get used to this table, it will make your life easier to fill out those values.